in here. All right. Chapter 9, Models of Chemical Bonding. And when we think about all the elements on the periodic table and we think about them as atoms, whether it's a hydrogen atom or a magnesium atom or a rhodium or a ruthenium or a palladium, whatever atom we think about on the periodic table, do atoms exist by themselves, just a single atom? Well, I would say not very often because atoms are so small. Okay, atoms are almost always involved in some kind of bond. And so in this chapter, we're going to talk about the three types of bonding: ionic bonding, covalent bonding, and metallic bonding. But before we really get into what those three types of bonding are, I want to talk about metals and nonmetals a little bit. So this takes us all the way back to just looking at the periodic table. And I told you a long time ago that the left-hand 2/3 of the periodic table, these are the metals. These are everything that are highlighted in blue. The upper right 1/3 of the periodic table, what's highlighted in yellow, these are the nonmetals: nitrogen, oxygen, carbon, things like that, the halogens. Okay, hydrogen, note that hydrogen is a nonmetal. That's why it's shown over here like that. Anyhow, so we have nonmetals over there, and then of course we have the metalloids that fall along the metalloid line. Anyhow, if I draw your attention to this table down here, if we think about these properties: atomic size, effective nuclear charge, ionization energy, and electron affinity, and if we think about them just with respect to metal atoms. So what's the deal with metal atoms? Well, we know that generally speaking, metals have larger sizes than nonmetals. And why is that? That's because atomic size decreases as you go from left to right across the periodic table. Now, why does that happen? The reason that happens is because the effective nuclear charge of metals is going to be lower, right, than it is for nonmetals. Again, same rationale. We said that effective nuclear charge increases as you go from left to right across the periodic table. What else? It says here that metal atoms have lower ionization energies than nonmetals. What's ionization energy? It's the amount of energy required to remove 1 mole of electrons from 1 mole of an atom in the gaseous state. And then finally, the electron affinity is less negative, okay, for a metal than it is for a nonmetal. And if you're like, what's your point, Mr. Dion? Well, my point is this: if you put all of this stuff together, all of these, 4 characteristics of metals together, what that means is that metals, generally speaking, like to lose electrons, right? They want to lose electrons because they're so big, okay? They have these valence electrons that are far away from the nucleus. They don't have a high effective nuclear charge, so the outer electrons, the valence electrons, aren't held very tightly, okay? And the ionization energy, the amount of energy that's required to remove an electron, isn't even all that high, okay? So metals like to, what's our take-home message, right? Metals like to lose, where's my pen? Metals like to lose electrons, okay? Metals like to lose electrons. Now, conversely, if we just flip it over and think about nonmetals, well, nonmetals are smaller, and the reason that they're smaller is because we know that effective nuclear charge increases as we go from left to right, and of course that's going to rein in the outer electrons even more. The ionization energies are higher, and so they don't want to lose electrons, right? And then the electron affinity is even more negative, and more negative refers to more energy is released. They achieve an even more stable state when electrons are gained. And if you're like, okay, what's your point, Mr. Dion? What are you going at here? What I'm getting at here is that nonmetals tend to gain. They tend to gain electrons. So I could have just said that to you, just said, okay, 1401, everybody that's hearing my voice, just memorize this. Metals like to lose electrons, nonmetals like to gain electrons. But hey, we've studied all of these characteristics: atomic size, effective nuclear charge, ionization energy, electron affinity. So it's nice to kind of put it all together and say, okay, well, there's some rationale for this. And if metals like to lose electrons, that means that metals are going to form what? They're going to form cations. Okay? Metals are going to form cations. And if nonmetals like to gain electrons, they're going to form anions. Okay? They're going to form anions. Let's just think about this for a second. I hadn't planned on saying this to you guys, but let's just think about it. If you think about fluorine, right, fluoride, okay, you're all aware of what fluoride is by now. We're used to seeing F minus. right? We're used to seeing that. And why does that happen? Because we know that if fluorine gains one electron, it becomes isoelectronic with a noble gas. So there's an example. What about something like sodium? Okay, sodium, you're used to seeing Na plus, right? The sodium cation. Why? Because if sodium loses one electron, it becomes isoelectronic with neon, right? And I can bounce, do the old bounce around here, right? It loses one electron, okay? Give me a thumbs up if you just follow me on this. This is just my introduction slide, just kind of showing you guys where we're going today and just getting started. Great, thanks, Isabel. Perfect. Great, thank you, Don. Awesome. Let's move on to the next slide. I think you're going to like this too. This slide just summarizes the 3 types of chemical bonding that all 1401 students have to be aware of. First one is ionic bonding. So ionic bonding involves the transfer of electrons and is usually observed when a metal bonds to a non-metal. An example, and I bet you if I asked anybody who's hearing my voice to give me an example, I know you could all cook up some kind of great example, but I'll just give you one here. If we have a sodium cation, sodium is a metal, and it bonds to a chloride anion, right? Chlorine is a non-metal, right? We're going to have an ionic compound, right? We would form NaCl. Okay, so probably not that much of a stretch for anybody who's here, right? Covalent bonding is another type of bonding, and it involves the sharing of electrons and is usually observed when a non-metal bonds to a non-metal. Let me give you an example of covalent bonding, okay? An example of that would be something like H2O. I bet you've all seen this somewhere in your travels. Has anybody seen water written with this angle like this before anywhere, and maybe a book, even perusing this book before? Yeah, so Violet says yes. So, okay, so some people have seen it around. And if you haven't seen it, don't stress. I mean, I did show you models with, the bent shape of water, but we'll get into molecular geometry even more later on. But what's my point is that hydrogen is a nonmetal and oxygen is a nonmetal. And so we don't draw a hydrogen ion and an oxygen ion. We show a bond, and this is a covalent bond that's formed between oxygen and hydrogen. Here's another covalent bond formed between oxygen and hydrogen. And finally, we have metallic bonding. Now, metallic bonding involves electron pooling and occurs when a metal bonds to another metal. An example of this would be something like an alloy. So say, for example, if you have brass, brass is an alloy, which is a mixture of metals. Brass is just a mixture of copper and zinc. Okay, so copper and zinc, and they're put together in the right proportion, and you get metallic bonding. Okay, and metallic bonding, it says here that it's when a metal bonds to another metal. It could be a different metal. It could be the same metal, right? So if you think about if you have just a chunk of iron, okay, or doesn't look very pretty. If you have a piece of iron, or if you had, I don't know, a piece of sodium, or if you had a piece of potassium, right? Those are all metals. And when all the atoms are aggregated together in that solid form, the metal, okay, that's called metallic bonding. Okay, so either one of those would be good examples of metallic bonding. All right, well, let's look at, some figures here. You know what they say, a picture is worth 1,000 words, right? So probably for some people, this might help clear up what I'm talking about. And this is just a pictorial form of what we just spoke about. If we have ionic bonding, so that's what's shown here in A, you notice that when the sodium atom, or when the sodium atom loses an electron, right, as it loses that electron, so subtract one electron, you get a sodium cation. Now, we talked about this at the very end of the last chapter, that the cation is going to be smaller. Why? Because the number of protons didn't change, but now we have less electrons. So those electrons are going to be reined in even tighter. Now, if we look at the chloride anion, what happens there? Well, the chloride gains an electron. It gains an electron. The chlorine, gains an electron, and it becomes chloride. Okay, and that's going to be bigger. Why? Because you've got the same number of protons, but now you've got more electrons. So there's less protons per electron to rein those in, and so it's going to have a bigger atomic or ionic radius, I should say. Anyhow, and if you're wondering, well, where does that electron from sodium, where does it go? And where does that electron that chlorine gets, where does it come from? Well, the electron that the chlorine gets actually comes from the sodium. That's what's being shown right here, right? Is the sodium is actually transferring its electron to the chlorine. think about this. It all goes together, okay? It is rational. Think about what I was saying a couple of slides ago. I said that a metal likes to lose electrons. Hey, that makes sense because I see the arrow going in this direction. I said that a non-metal likes to gain electrons. Well, that makes sense, okay, because the chlorine is taking an electron to become a chloride. Okay, now, if we have all these positive and negative charges, right, all these positive and negative ions, or these cations and anions, they can all bind together in this ionic solid. And you see how it has this beautiful arrangement where they alternate chloride and sodium, okay? And we call that an ionic solid. You'll hear me call that the crystal lattice. Right now, think about it. If I was to ask you, what's the molecular formula of sodium chloride? You wouldn't say, well, it's Na, I got 1, 2, 3. No, when we're talking about ionic solids, generally speaking, we give the empirical formula. And that's why the formula for sodium chloride is simply NaCl, right? We simplify it to the empirical formula, okay? All right, now I've probably talked about that quite a bit, but it's kind of exciting. So let's move on from there and talk about electron sharing or covalent bonding, which is shown in the second picture. Here we have a covalent bond formed between a chlorine and a bromine, and we're going to talk even more about this as the class progresses. But what the heck is going on here, right? Is that you have two nonmetals. Chlorine is a nonmetal, bromine is a nonmetal. Neither one of them is becoming an ion. Right? I don't see a chloride. I don't see a chloride here. I don't see a bromide here. No, what they're doing is they're sharing electrons and then they're forming a bond. This is the bond that's formed right there. That's the little line that's shown here. Now, one of the big differences between covalent bonding and ionic bonding is that now we have what? We have separate molecules, right? And so each one of those separate molecules is identical, but they're all separated, okay? Now, they can be close together, they can be far apart, depending on maybe the phase of matter or temperature, but the idea still stands that we have separate molecules, right? Each one of these is a ClBr molecule. Now, finally, we have the metallic bond, okay, the metallic bond, and that's shown here in C. This is just showing you sodium. And I like the way that she draws this, actually. It's kind of fun how she puts the kind of the nucleus, maybe, or the core of the atom here. And then you see how it's kind of like fuzzy around each one of those cores? Well, that shows you how all the orbitals of those sodium atoms, they all overlap with each other. And what that does is it kind of creates a conduit. If you're like, what's a conduit? A conduit is like you guys know what conduit is on the side of a wall if you're in like an industrial building or something? Conduit's like the pipes they put up the side of a wall to run wires through. Anyhow, whatever. The idea is that it kind of creates like a conduit so that an electron can move or be shared all around all of these atoms like that. Okay, so all the electrons are kind of shared. And that's what we call sometimes, let me delete that. We call that sometimes the electron sea. I'm not kidding, okay? It's even here in the book. It's called the electron sea. Anyhow, just a pictorial representation of the three types of bonding that we're interested in this chapter. All right, here's another figure. This is one of those things where I could spend way too much time on it, but I'll try to be brief here because I won't ask you any direct questions about a triangle, figure that we saw in chapter 9. But the point here is that she's saying, okay, well, you have gradations in bond type among period 3 and group 4A elements. And if you don't have a periodic table next to you, which you should, okay? So if you think about period 3, it's got sodium, magnesium, aluminum, silicon, phosphorus. I'm going to have to move down here, sulfur, chlorine, and argon. And then if you think about group 4A, so group 4A, one of my favorite groups, carbon, silicon, germanium, tin, and lead. So these are the elements, most of the elements that you see on here. Okay, if you think about just the elements themselves, that's shown over here on this side, okay? So we start with, pure chlorine or pure sulfur or pure phosphorus, right? And as we go I'm just looking at this line here, as we go from, this would be going from right to left across the periodic table, what's going to happen? Metallic character will increase, okay? Now, if you look at this group right here, as we go down a group like that, well, what's going to happen? Atomic size is going to get bigger and bigger and bigger as we go down a group or a family. And so they're going to have more metallic character, right? They're going to be more willing to lose electrons and form cations. Okay, so that's what's going on here. Now, if you look at, let's say, if we look at this part over here, um, you can see that we're going from, so this is period 3, right? These are all elements of period 3, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and then they're all bound to chlorine. Okay, so they're all different chlorides like that. Okay, and you can see that as we have a metal and a non-metal, and then all the way down to 2 non-metals, it becomes more and more covalent and less ionic. And then what the heck is going on in the last axis? Let me take a look. Let's see here. This one here is you're combining sodium with different metals. So here you have just pure sodium next to itself, and it's next to magnesium. So you have pure metallic character, and then as you go across until it's bound to a non-metal, you get more ionic character. Anyhow, this is the kind of table that is just all that you really need to understand about this table is the rationale for when is something going to be covalent, when is something metallic, and when is something ionic. But this is kind of like the third iteration of the same concept that we've looked at today. All right, let's switch gears just for a second here. Yes, I did say second. Let's talk about Lewis electron-dot symbols. You're going to like this. I hope you do, because next chapter we're going to look at Lewis structures, and for that we'll have to use these dot symbols, Avogadro's number of times. It says here, to draw what's called the Lewis symbol for any main group element. What's a main group element? Okay, not a trick question. This is just a review question. Remember, a main group element is an element from the S or P block. Okay, so this is S and, maybe I shouldn't have put S or, up to S and P block elements. So not the transition metals, not the lanthanides, not the actinides, the main group elements. You look at the A group number, so group 1A, 2A, 3A, 4A, 5A, 6A, 7A, so on and so forth. And that gives you the number of valence electrons. That's not really anything new to anybody who's been coming to class. That's review. Okay, if you think about sodium, it's in group 1A, so of course it has 1 valence electron. If you have oxygen, it's in group 6A, and so it has 6 valence electrons, right? What we do is we place a dot, 1 dot at a time, on each of the 4 sides of the elemental or the element symbol, and that represents, or each one of those dots is going to represent a valence electron. Okay, keep adding dots, pairing them up until all are used up. So for example, if you look at nitrogen, nitrogen is in group 5A, right? Family 5A. What does the 5 mean? It has 5 valence electrons. So this is the way I do it. I'll show it to you in real time. I draw the nitrogen like this. You can start on any one of the 4 sides you want. I don't care about that. But the idea is that you have 1 unpaired electron, 2, 3, 4. So the first 4 electrons, you always get them as far away from each other as possible. That means on all 4 sides of the element symbol, you'll have an unpaired electron. Now I need to have 5 electrons, and so the last one can pair up with any of them. And you can see that manifested here, okay? I can put it on the right side, I can put it on the bottom, I can put it on the left side, or I could put it on the top, okay? Either way is totally fine with Mr. Dion. He's not going to give you a hard time about that, okay? So there we go. That's a Lewis dot symbol. Give me a thumbs up if you follow me on the Lewis dot symbol. Just number of electrons, valence electrons, dots around. Yep, okay, thanks, Isabel. Good. All right. Yeah, great. Wonderful. Good. Okay, and don't worry, this isn't the last time I'm going to talk about Lewis electron dot symbols. I'm not going to try to surprise or anything. It says here, for a metal, now, right here, we're talking about some of the significance of these valence electrons, okay? Because right now you might be thinking, okay, Mr. Dion, I got a symbol and I got some dots. Great. Okay, what can I do with that? Well, hold on. It says here, for a metal, like sodium, for example, or magnesium, the total number of dots in the Lewis symbol is the number of electrons that it loses to form a cation. Well, that's not really that much of a stretch. If we look at magnesium, okay, let's pick magnesium just off the top of my head. Magnesium is in group 2A. So if magnesium is in group 2A, that means it's got 2 valence electrons. How would I represent them? I could put them like this, like that. That's fine. If you are like, I want to put them like this, I think that's weird, but okay. Anyhow, I'll put them back the way that I like them on each side like that. Now look, it's not meant to be anything complicated. It says the number of dots, 1, 2, is equal to the number of electrons that it's going to lose to form a cation. Well, that's not a surprise, right? We know that magnesium likes to lose 2 electrons to become magnesium 2 plus. I'll balance that out. Okay, not a stretch there. What about a nonmetal? It says here for a nonmetal, the number of unpaired dots equals the number of electrons it gains to form an anion, or the number it shares to form covalent bonds. Let me give you an example of the first bullet point there. If we think about oxygen, okay, oxygen is in group 6A, so it's going to have 1, 2, 3, 4, 5, 6, like that. Now, how many unpaired dots are there? There's 1, 2. And it says here the number of unpaired dots equals the number of electrons it gains to form an anion. Well, hey, that's not a stretch for anybody. Everybody in this class by now should know that oxygen likes to gain 2 electrons to become isoelectronic with neon. Well, look, there's 1, 2 electrons. Hey, nothing new there, right? So add 2 electrons and you end up with the oxide, right? O2 minus. Okay. Now I didn't put in my valence electrons. Maybe I should put them all here. Okay, to show you that now you have a total of 8 and you have a 2 minus charge like that. Another way to think about it, that is it says, or the number that it shares to form covalent bonds. Think about the molecule H2O that I drew earlier on. Okay, if I just draw the structure of H2O, and don't worry, we're going to go over in detail later on in this class how to draw this. What all you need to understand is that it shares 2 bonds with 2 hydrogen atoms. So hey, it's all working out. I want to cover what's called the octet rule with you. I bet you that if you studied high school chemistry, which I know many of you have, I bet you would have heard of the octet rule. And the octet rule states that when atoms bond, they lose, gain, or share electrons so that they attain a filled outer level of 8 electrons. And the 8 electrons, that's what we call an octet, right? Octet, okay, is having 8 filled outer level of 8 electrons. Another way to say that is almost like regurgitating this rule. It's not exactly the same, but it's pretty darn close. Okay, or hold on, where was it? It's not the rule I'm looking for. I forget where it is, but anyhow, the octet rule is kind of like another way of saying this. Okay, this is what I was getting at, is that atoms will do whatever they have to do to be like a noble gas. Okay, so there is an exception to that. Okay, there is an exception to the octet rule, and that is if you have an atom, or sorry, if you have an ion that's isoelectronic with helium. Well, helium only has a 1s orbital available, and an s orbital can only hold 2 electrons. So in that case, you'd only have two electrons, and you'd be isoelectronic with helium. I don't know if the word is in our book or not, but that's actually called a duet. It's not a joke. Okay, you have an octet and a duet. So say, for example, if you have lithium, okay, well, lithium is in group 1A, so we know that lithium likes to form a lithium cation like this. Okay, well, what's the electron configuration of a lithium cation? It's just going to be 1s2. Okay, so that's isoelectronic with a noble gas, which is helium. Okay, anyhow, let's move on. It says here Lewis dot symbols for some elements. There's something I don't like about this slide. There's one thing on this slide that kind of rubs this guy the wrong way. Okay, and so you see how she says here, okay, well, I got a group 1A. Oops, I meant my highlighter. I got 1A, 2A, 3A. And then she just puts the number of dots around it like that. The only one here that kind of irks me, and you're like, Mr. Dan, you're too picky, are these two right here. I mean, they're totally right. If a student drew that, I would say that's totally fine. Just personally, I don't like to draw oxygen or sulfur that way. I would draw it. I like to maximize the distance between unpaired and paired electrons. So I would draw my oxygen like this, having the unpaired electrons further away. I don't dig that. Okay, so I would draw the sulfur the same way. Again, that is just me being picky. But hey, all right. Anyhow, there we go. Give me a thumbs up if you think you could draw these Lewis dot symbols. Not meant to be, probably the hardest thing we've looked at, but it's something new probably for most people who are here. Great. All right, yuppers. I'll take it. I'll take that yuppers to the bank. Good. Okay, well, let's move on from there and let's talk about ionic bonding. You notice how this chapter kind of flips around, 1 minute we're talking about ions, then we're going to covalent, then we're talking about metals. But anyhow, the idea is that she keeps, going on the same subjects over and over and over. Anyhow, it says here, an ionic bond is formed when a metal transfers electrons to a nonmetal to form ions. Okay, we've talked about that quite a bit already. Then the ions, the cation and the anion, well, we know the opposites attract, and then they're going to attract each other, and they're going to form a solid compound. We talked about a crystal lattice. The total number of electrons lost by the metal is going to equal the total number of electrons gained by the non-metal, okay? Now, I know that you probably follow me on what's going on here, because if I was to give you this, okay, let's just take a step back in time, way back to when we were working on nomenclature. If I was to give you this lithium fluoride, okay, this would be a perfectly legit exam question from exam 1 or midterm 1. If I said, what is the correct formula for lithium fluoride? You'd say, well, I know it's an ionic compound, so it's going to be LiF, okay? That's something that you should all be able to do, okay? Just come up with the formula just like that. Johnny on the spot, no problem, okay? But now that you've learned how to name the compound, I want to take a look at the electron configuration and how it relates to the way the compound is formed, okay? So if we look at the electron configuration of lithium, everybody should be able to whip that up, okay? Everybody should be able to whip up the electron configuration of fluorine, okay? No problem, no problem. Well, let's take a close look at the orbital diagrams, okay, which are shown down here. Okay, here they are. Now think about this. If the lithium becomes a cation, right, which it's going to do, it's going to have to lose one electron. Look what happens if that, and pay close attention, this is really interesting, and for some of you it might seem very simple, but I don't want you to just blow me off and say, okay, it's too simple, Mr. Dion, I get it. Hold on, just watch carefully, because this is very cool. Look at that electron that's in that 2s orbital, okay, from our 1s2, 2s1 in our lithium metal. When it loses that electron, look where it goes. It's going to go into the 2p orbital of the fluorine. Now, this is something we haven't looked at before. Why the heck would it go into that specific orbital? Why didn't you just say that fluorine just gains an electron? Well, hold on. We got to be specific here, because now look at this. This is the beautiful part. Look at this valence shell. I don't know why I underlined the 1s. Look at this valence shell of our fluorine. Look, can you count? 1, 2, 3, 4, 5, 6, 7, 8. A full octet. And if you're thinking, okay, Mr. Dion, I know it's isoelectronic with a noble gas. I get it. Okay, sure, I know you get it, but I just want you to look at the orbital diagram with me. Excuse me. All right. Who finds this interesting? Just me? Am I the only person who's interested about this? Because I already knew this. Okay, one person. All right, cool. I do. I think it's really interesting. You know, and these fundamentals are going to be crucial to understanding what's called hybridization. I'll just put that kind of a word in your ear that we're going to learn, probably a few weeks from now. So it's pretty fascinating here. So now, not only does the fluoride have a full octet in its valence shell, look at this. The lithium is isoelectronic with helium. It's got a duet, okay, a full duet. It's beautiful. It's really a beautiful thing. All right. Anyhow, I'm surprised that only one person was excited, but okay. Mr. Dion's going to take that up with his therapist. Okay, I'll have to hire one. All right, let's try a problem here. Who wants to try a problem? Just me? I bet everybody wants to try a problem by now. Like, I've been listening to you yammer on for 25 minutes. All right. It's just 10 a.m. on a Monday. Well, take another sip of coffee and let's give one a try here. This is a fun problem. It says here, use partial orbital diagrams and Lewis symbols to depict the formation of sodium and oxide ions from the atoms and determine the formula of the compound form. Now look, I know you all know what compound is formed from sodium and oxygen, right? I know that by now, or at least I hope by now, you know that sodium forms a +1 ion, oxygen forms a 2- anion, and so they're going to form this sodium oxide. Right? That's not meant to be anything new for anybody who's hearing my voice. What we want to do, though, and we're just going to do this once, okay, is we're just going to draw it out in terms of the orbitals. Okay, so let's draw out partial orbital diagrams for sodium. And if I start with my sodium, and I'm just going to do the valence electron. So sodium has a 3s orbital. I'm going to draw all the orbitals because that's the way that Silberberg does it. So there's our sodium. Of course, there's, and again, I'm just probably going over way too much detail here, but by now you know that sodium is neon, is the core, and then 3s1. So I'm just drawing the valence orbitals, nothing else, okay? So we have sodium, that's 3s1. We're going to need 2 sodium. So I'm going to put a second sodium down here. So we have another sodium atom like that. Okay, 3p. By now, you should know that oxygen, and I'm kind of running out of space here, but oxygen is helium, or the core electrons, and then we have 2s2, 2p4. So I'll draw the oxygen right here. I'll draw the 2s and then the 2p. So 3 types of p orbitals, right? You guys remember Ml? Yes. All right, there we go. So look, we know that 2 sodiums are going to combine with 1 oxygen. Well, look what's going to happen. Look at this. Each one of those electrons is going to end up in a p orbital. Okay. Maybe I'll draw an arrow like this. Okay, like that. And then what are we going to end up with? We're going to end up with sodium cations. Okay, we're going to end up with sodium cations. They have nothing in the 3s orbital, nothing in the 3p orbital. Okay, we're going to have another sodium that's got nothing in the 3s orbital, nothing in the 3p orbital. Okay, and then we're going to have our oxygen, which is now O2 minus, which is going to have a full 2s orbital, and it's going to have a full 2p orbital. 2 times 4 orbitals total gives us 8. That's a full octet. And if you're like, what about the octet of this guy? Well, hold on. When sodium lost that electron, okay, when sodium lost that electron, it became isoelectronic with neon. All right. So there you go. They're both isoelectronic with a noble gas. Okay. Give me a thumbs up if you follow me on that. Cha-cha. All right. There we go. Great. Wonderful. Wonderful. Okay, well, let's move on from here. This is kind of a fun slide right here. Oh, this is just the solution worked out by Dr. Silberberg. This is showing the exothermic reaction when you react sodium metal with bromine. So bromine is a liquid. I think I've told you that bromine is a liquid. So in here, in this flask, this is called a Florence flask, you have Br2 liquid. Now, it's got a really high vapor pressure, and if you don't know what vapor pressure means, it means it like boils really easily. So there's liquid down here. You can't see. It's a little pool down here. And then there's some bromine gas up here as well. It's really dark red. And then these are pieces of sodium. I don't know if you guys are joking, but I hope you are. Okay, so that's not a good looking drink. Definitely not. Okay, so here's sodium metal. So this is solid sodium, and this is oil on top. So this is how we store the sodium. But if you took a pair of forceps, which is the chemist's way of saying tweezers, can I draw tweezers? Is this a pair of tweezers? I don't know, something like that. If you were to grab one of those pieces of sodium and then whoop, plop it in there, I wouldn't want to be the guy to do that. I mean, it probably wouldn't hurt you, I suppose, but you notice how they put a piece of glass tubing on here to allow gases to escape. So this is an exothermic reaction. What does that mean? Essentially, it means that heat is given off when you react these two together. Well, what's happening is when you react sodium, which is a group 1A metal, with bromine, which is a group 7A nonmetal, the sodium is going to form a sodium cation, right? You're going to have a sodium cation, and you're going to have a bromide anide, and they're going to react to form what? Sodium bromide, which is a solid. Okay, there we go. Now, we're going to talk just for a second here about the Born-Haber cycle. Sometimes it's pronounced the Born-Haber cycle. I guess it depends on who you're talking to. I don't ask any questions on the exam about the Born-Haber cycle on the next exam because they're pretty laborious, but I think I put a few questions in it in the homework. And so, because I know you have more time to work on the homework, but the Born-Haber cycle is just a way of measuring lattice energy. So, and if you're like, what the heck is lattice energy? The lattice energy is the energy that's released. So this here is the lattice energy right there. Is the energy that's released. So you see how the delta H here is negative. So delta H stands for enthalpy, which is the heat released from a reaction at constant pressure. And we'll talk about that more in chapter 6, but I digress. So lattice energy is the measured energy of when you take the ions in the gaseous phase and they come together and they make the solid. So you see here that lattice energy is lithium cation in the gaseous phase plus the fluoride anion in the gaseous phase, and we end up with solid lithium fluoride. Now, you might be thinking, well, how in the heck do I get lithium in the gaseous phase? Like, what do I do? How do I get, well, fluorine's a gas, that might not be that bad. But what if I want to make sodium chloride? How do I get sodium in the gaseous phase? Like, what do I do? I have to atomize this or something, or heat it up? Well, in fact, lattice energies are pretty darn tough to measure directly. And so Born and Haber, they came up with a way of measuring that indirectly. Okay. And what they did is they said, okay, well, if you start out with solid lithium, so that's lithium, just atomic, sorry, lithium metal plus fluorine. Well, if I add 1 mole of lithium plus a half a mole of fluorine, okay, that's going to give me lithium fluoride, right? That's just the equation for the formation of lithium fluoride. You take lithium, which is a solid in its standard state, plus 1/2 of a mole of F2. That's a gas in its standard state, and we'd end up with lithium fluoride like that. Okay, but that's not the lattice energy, right? That's it not being formed from ions. That's it, the compound lithium fluoride being formed from the elements in their standard state. So how do we get to that lattice energy? Like, where are you going with this, Mr. Dan? Well, hold on. What you can do is you can use ionization energies, heats of vaporization, heats of sublimation, and electron affinities in order to calculate the amount of energy that it takes to get these elements in the gaseous phase. Okay? And so the way that we would do that, for example, is you'd start with lithium. Let me back up here a little bit more, maybe. Okay, so you'd start with lithium. And first, you'd want to get that into the gaseous phase. Okay, so that's the first step. The next step would be to break the fluorine because we have F2 and we only need 1 fluorine atom. So we break F2 like that. So this is the bond dissociation energy here. Then we have to ionize lithium. So we have our lithium and we want to convert it into a lithium cation. That's the ionization energy. We have to make an anion from fluorine. That's the electron affinity. And there we go. Once you add up all of those enthalpies, okay, all of those amounts of heat required or released, okay, you end up with this level here, okay? And then what you're going to do is you're going to compare that to the amount of enthalpy that the solid has, and then you're going to get the lattice energy like that. Probably confusing the way that I'm explaining it right now. I think the best thing to do with this, with the Born-Haber cycle, would be to look at a problem to make it more clear. I don't have, now that I'm looking at my notes, I don't have a problem actually highlighted. I don't even think I have a problem in my notes. And so I'll have to come up with one and we'll take a look at one. Tell you what, we'll take a look at one before put it this way, in plenty of time. Okay, in plenty of time. We'll take a look at a question like that. Okay. But in chapter 9, the way that we think about lattice energy is more qualitative, okay, rather than, I'd say, semi-quantitative and qualitative. If you're like, what do you mean by that? Well, again, the lattice energy, okay, so the lattice energy, right, we think of ionic compounds, right, ionic bonds, right, we form a crystal lattice. The lattice energy is the strength of the solid's ionic bonds, okay? So if you compare sodium chloride and sodium bromide, which one of them has a stronger electrostatic interaction between the cations and the anions? Well, how would we figure that out? It says here that the lattice energy, or the enthalpy of the lattice, is dependent upon the charges of the ions and the distance between the nuclei of the atoms. So the greater the charges, the larger the enthalpy of the lattice energy is going to be, and the smaller the distance between the atoms, or the smaller the atomic radii, or ionic radii, I should say, the larger the lattice energy. And if you're like, what is the point of all this? Okay, if you understand this formula here, okay, and you should know what the heck is going on here. The lattice energy is proportional to the electrostatic interaction between the cation and the anion. So this is just a version of Coulomb's law. So again, the lattice energy is going to be equal to some kind of constant, K, don't worry about that, multiplied by the product of the charges. So this is the charge of the anion, okay, times the charge of the cation. You can just assume it's an absolute value here because you're always going to end up with a negative number. And then you're going to divide that by the distance, okay, between the two nuclei. So what does that mean? It means that if you have, the bigger the number is here, the bigger this number is going to be, right? The higher the charge you have on your cation and anion, the higher the lattice energy. What else does it mean? It means that the smaller the distance between your anion and your cation, right? The smaller the denominator gets, the bigger this number is going to get, okay? So in order to have a really big lattice energy or a strong lattice or a high lattice energy, you've got to have what? High charges and a small distance or a short distance between the anion and the cation. Look, give me a thumbs up if you just follow me on the rationale for the formula. Just the rationale. Just numerator and denominator, getting the strongest lattice energy possible. Okay, good. All right, we got a few people that are with me here. Okay, well, let's look at a problem that I could ask. Okay, let's look at the kind of problem I could ask here. And what does it say? All kinds of stuff. It says here, use ionic properties. Okay, this is a great problem. Use ionic properties to explain which compound in each pair has the larger lattice energy. Rubidium iodide, sodium bromide, that's part A. And then the second part, potassium chloride or calcium sulfide. Okay, let's do the first one, rubidium iodide, sodium bromide. Start with that. We've got we got rubidium iodide versus sodium bromide. Now remember our formula, that delta H naught of the lattice, which is just a way of saying lattice energy is equal to, or you could say it's proportional to the electrostatic interaction. It doesn't matter. The whole point, we'll just put it like this, is proportional to K times Q1. And we'll put Q anion times Q of cation divided by the distance of anion to cation. Okay, let's think about this very carefully. The first thing I notice here is that both of the metals are in group 1A. Right, so rubidium is going to form a +1 charge, and sodium is going to form a +1 charge. Did anybody notice what the relationship is between iodine and bromine? Can anybody tell me what the relationship is between these two? They're in the same what? What do they have in common? Yeah, exactly. They're in the same group, right? They're in the same family or the same group. Thanks, Joel. Thanks, Violet. Perfect. Right, so that means that iodine is going to have a -1 charge, okay? And bromide is also going to have a -1 charge, like that. Okay. So what does that mean? That means that if we were to plug the charges, which are +1 and -1, and +1 and -1, they're both going to be the same. So the numerator is the exact same in both of these cases. So that means we cannot solve it using the numerator. We can't solve this problem. We're going to have to use what? We're going to have to solve this problem based on the distance between the anion and the cation. So whichever one of these pairs has the smaller cation and anion is going to have the stronger or the higher lattice energy. Now, let's examine the two metals again. We've got rubidium and sodium. Sodium is in period 3 and rubidium is in period 5. So sodium is smaller, right? Sodium is smaller than rubidium. Let's look at bromide and iodine. Okay, so if we look at, you could look at iodine and bromine, or just think about iodine and bromide. If we compare those two, well, remember that atomic and ionic size for the same charge will get bigger and bigger and bigger as we go down a group. And so bromide or bromine is going to be smaller. Both of them would be smaller than iodine or iodide or iodine. Okay, and so this one is going to be smaller. Okay, so both of these are smaller. Both the cation in sodium bromide and the anion in sodium bromide, they're both smaller. And so that means the distance, so if we put here distance of RBI is going to be greater than distance of sodium bromide. Okay, and remember, the smaller the denominator, the higher this number. And therefore, the greater lattice energy is going to be sodium bromide, has greater lattice energy. Okay, that was probably a lot of talking to solve the problem that I'm sure many of you found rather simple, but I think it's worth going over that in detail. Let's try the next one. Take some room here. The next one is potassium chloride and calcium sulfide. So we got potassium chloride and we've got calcium sulfide. Does anybody have an inkling which one of these would have a stronger lattice energy or a higher lattice energy? I'm wondering if anybody could solve this one kind of quickly. No? Okay, well, if nobody's sure, you guys hear me? Okay, okay, good. All right. Okay, I'm getting a mixture here. First, let's evaluate the charges. All right, for our cation, we're going to have K plus, and we're going to have calcium 2 plus. For our anion, we've got chloride minus, and we've got sulfide 2 minus. Well, already you can see that +1 and -1 versus +2 and -2, right? 2 times 2 is 4 times bigger than 1 times 1, right? 2 times 2 is 4. And so automatically, you can see that the denominator is going to be much larger. It's going to be 4 times larger. And they're all of these ions, they're all isoelectronic with argon. So all ions isoelectronic with argon, like that. Okay, and since we've got much higher charges here, we're going to have a higher lattice energy. So higher lattice energy, just like that. All right, let's move on from there. Here's her solution. I never refer to her solutions, but it says size decreases from left to right. So potassium is slightly larger than calcium. Sulfide is slightly larger than chloride. However, these small differences, and pay attention here, are not nearly as important as the charges, okay? The 2 plus and the 2 minus charges, which have twice the charge of potassium and chloride, and so calcium sulfide has the larger lattice energy. All right, there we go. So when it comes down between a battle between charge and size, charge wins, okay? There we go. All right, let's talk about some properties of ionic compounds for a few minutes. What time is it? 10:17. How many minutes do we have left? Time's class end. I think it ends around 12:30, something like that. Okay. All right. I'm just getting started. Like 1 p.m. Yeah, be nice. Anyhow, let's keep going. Since here, the ionic compounds tend to be hard, rigid, and brittle with high melting points. And you think about, every restaurant in North America, maybe the world, when you go to any restaurant, they always have an ionic compound on the table. In fact, if they don't, you're like, where's the salt? That's kind of strange. But you're aware that sodium chloride has a really high melting point, right? Has anybody here ever tried to melt sugar before on the stove? Like sugar, table sugar, to make a caramel sauce? Violet, how difficult is it to melt sugar? Not very difficult, right? You turn on the stove and sugar melts very quickly. But sugar is made completely of nonmetals. They're all bound together covalently, okay? Whereas sodium chloride, has anybody ever tried to melt sodium chloride? Well, it's not going to work because sodium chloride has a much higher melting point because it's ionic, right? The electrostatic interaction between that sodium cation and chloride anion is so strong that it's really hard to melt, okay? You're probably also aware of the fact that ionic compounds like sodium chloride are hard for the most part, rigid, meaning they don't bend, hard means they don't dent, and brittle means that they can break with like a fracture. Anyhow, ionic compounds also do not conduct electricity in the solid state. Okay, in the solid state, the ions are fixed in place in the lattice and do not move. Okay, so this is important. that we can't conduct electricity with an ionic compound in the solid state. Ionic compounds conduct electricity if they're melted or if they're dissolved, because if they're melted or dissolved, then the ions, the cations and anions, are free to move and they can carry a current. Let me show you a slide that's kind of a fun one here. It says here, why ionic compounds crack. Now you can imagine this as being lithium bromide or sodium chloride, whatever, it doesn't matter. But the idea is that you've got a +1 and a -1 charge. You see how they alternate here? They alternate like that, back and forth, back and forth, back and forth, back and forth. Okay, well, if we take a hammer or some kind of force and we just hit this part of the ionic compound like that, it's going to cause some movement, in this part, okay, this part of the ionic solid like that. And then all of a sudden, the like charges are going to be next to each other like that. And then they repel each other. And then boom, you get a crack like that. Isn't that cool? Pretty neat, huh? Give me a thumbs up if you think that's cool. I think it's cool. Anyhow, I think it's very interesting. All right, anyhow. Yeah, so that's why ionic solids are so brittle. It's kind of neat in case you didn't know. I mean, I didn't know until I studied chemistry. The next slide is another kind of just a fun, figure that she has in the book. It says here, if you take, so this is, and I think I showed you this before when we talked about electrolytes and non-electrolytes, right? This is just a light bulb. Here's the cord, and these are 2 electrodes. And in order for the light bulb to light up, in order for a current to pass through the filament, you've got to be able to pass a current in this beaker, right? So you can get electrons to flow from the anode to the cathode. And it's just showing you that if you put the electrode in a solid ionic compound like solid sodium chloride, you get no current. If you melt it, so you can see here that the way that and if you're like, how the heck are they melting it? The way that they're melting it is that they're using, you see there's a Bunsen burner right here. This is a clay triangle, okay? And it's on an iron ring here. And this is called a crucible. Okay, so they stuck the electrodes in the crucible and they heat the living tar out of it, I guess, with this Bunsen burner. And they might even use something like a Meeker burner. Anyhow, but they melt it, and then you have the ions mobile, and so it can conduct electricity. Also, we talked about this earlier on in the class. We said if we have an ionic compound dissolved in water, you can see the ions are free to move like that, and so we have conduction of electricity. Kind of a fun slide. All right, but something to be learned there. Also, this shows you just some relative, melting points and boiling points of some ionic compounds. If you compare, let's just pick a couple here. I mean, we could sit here and ramble on about this all day, but I know you didn't come here for that. If you compare sodium iodide and sodium chloride, well, they both have the same charges, right? Both are +1 and -1, the cation and the anion. What's the difference? Why does sodium chloride have a higher boiling point, or sorry, a higher melting point and a higher boiling point than sodium iodide? It's going to be based on the size of what? The anion, right? Iodide is bigger, and so the bond is bigger, and therefore the denominator is bigger. And the denominator is bigger, and so therefore the lattice energy is going to be smaller, and therefore it's going to take less energy to melt it. Let me think of another example here. I don't know. If you compare lithium fluoride and magnesium oxide, for example, all the cations and anions are pretty close to the same size, right? You think about lithium, lithium and magnesium. I guess there is a difference in size, but it's not huge, And then you have fluorine and oxygen. Well, they're fluoride and oxide. They're both isoelectronic with neon. But what's the difference here is that here you have a +2 and a -2 charge, and here you have a +1 and a -1, right? And we said that the charge is going to dominate, and you can see how, the melting point and boiling point of magnesium oxide is much higher than that of lithium fluoride, right? And if you're like, well, how are you figuring this out, Mr. Dean? All I'm using is that same old formula that we had earlier on, the delta H lattice, or if you want to write energy of lattice, if you just want to write energy of lattice, just to kind of figure it out, qualitatively or semi-quantitatively, you just put charge of anion, charge of cation divided by the distance between the two, like that. Anyhow, just more kind of information here. All right. Has anybody here taken a face-to-face lab and ever seen a CRC handbook before? You guys know what a CRC handbook is? The CRC handbook. One of my students bought one time. I mean, I've taught thousands of students, and only one student I ever had bought a hard copy of it because it's a huge book, bigger than a dictionary. Nobody, yeah. So one person has seen it. Anyhow, Megan has seen it before. Anyhow, if you look at the compounds that are, so if you're like wondering what the heck is a CRC, Mr. Dion, before you start talking about it, the CRC handbook is called the Chemical Rubber Company handbook, and it's still in publication. It's a handbook that's used to find all kinds of physical properties and chemical properties of all kinds of different ionic and covalent compounds. And what I'm getting at is this: it's a big book, okay? Big book. If you look at this big book and you look up the number of ionic compounds, there's actually not that many ionic compounds in there compared to covalent compounds. The number of covalent compounds dwarfs the number of ionic compounds. Okay, many more covalent compounds. All right, and so it's crucial that you understand covalent bonding. And we're going to start by looking at the covalent bonding in the simplest possible covalent molecule, and that is a hydrogen molecule, right? H2 molecule. You have two atoms of hydrogen. If we start over here on the far right, you've got an atom of hydrogen here and an atom of hydrogen here. And what's happening is you're bringing those two hydrogen atoms closer and closer together. And what's going to happen is you're going to get to a point where you see these two arrows pointing like this. What those are referring to is that the nucleus of each one of those atoms is going to start attracting the electron of the other atom. You're like, okay, well, I guess a nucleus is going to start attracting the other electron, but isn't there going to be repulsion between the two nuclei and the two electrons? Yes, there will be. But the point is this, is that the two atoms of hydrogen are going to come closer and closer and closer and closer together, okay? And they're going to come so close that they're going to attain this lowest energy, okay, this lowest energy state, and that state is this state shown right here. And what you need to know about this state is that is the state that represents, or the distance between the two nuclei then represents a covalent bond, okay, between the two hydrogens. And what's happening here, it's showing you that the attraction between the electrons and the nuclei are maximized, and the repulsion between the nuclei to the other nucleus and the two electrons are minimized. So our attractive forces are maximized and our repulsive forces are minimized. Now again, when it gets to that state, that is where it has the lowest potential energy and is therefore going to be the most stable. Okay? If at this point we measure the distance between the two nuclei right here at number 3, that is called the bond length, okay? And it just happens to be 74 picometers. Okay, you don't have to have that number memorized. Also, if you measure the amount of energy that's released when you form that bond, it's 432 kilojoules per mole, okay? That's what's on the y-axis here. And so what does that tell you? That tells you that if you want to break apart 1 mole of H2 molecules into separate atoms of hydrogen, it's going to cost you 432 kilojoules. All right? There's a reason why the two atoms come together. If you're like, why can't they just be happy by themselves? The reason why, and I'm repeating myself, but whatever. The reason why they come together, why do they do this, is because they achieve a lower energy state. Okay? Right? That is why you end up forming the bond. Right? The lowest potential energy is going to be more stable than when the atoms are just by themselves like that. Now, if you were to keep going, if you start pushing the atoms together like that, you can see that the potential energy just increases dramatically, very quickly. Right? Why? Because then you're going to be pushing the nuclei too close together and they're going to repel each other. Okay? Anyhow, there we go. Now, if you were to yeah, anyhow, that's enough. I won't say too much. I don't want to I don't want to make something, more complicated than it needs to be. This shows the electron distribution. We have a contour map and a relief map here for the hydrogen molecule. So if you look at the contour map in A, it says here that electron density, the blue shading, is high around in between the two nuclei. The electron density doubles with each concentric curve. Okay, and so what's going on here is that if you're unsure as to what's being shown in this slide, which maybe it's not even all that clear. I didn't mean to do that. Okay, there we go. So this is just showing you a map, an electron density map of the H2, right? So this is a hydrogen. This is a hydrogen here. It's showing you the nuclei. And you can see, like, the take-home message from this slide is nothing more than the electrons spend most of their time, around and in between the two nuclei. You can really see that here in this relief map. It's the same thing. You have the two hydrogen atoms like that, and you can again see that the electrons spend most of their time in between the two nuclei and around the nuclei, like that. All right, there we go. Da-da-da. Nothing more than that on that slide. All right, let's talk about bonding pairs and lone pairs. So this goes back to that whole Lewis dot symbol that we looked at earlier on today. And you need to know what bonding pairs and lone pairs are. It says here that atoms share electrons to achieve a full outer level of electrons. The shared electrons are called a shared pair or a bonding pair. The shared pair is represented as a pair of dots or a line. Let's go back, and you might be sick of talking about this slide, but I want to talk about it again. Okay. When you have the two hydrogen atoms, if we were to draw the Lewis structure of a hydrogen atom, you have one with a dot like that, and then you have another one with a dot like that. I'm going to move this dot over here just for simplicity's sake. Okay, you see how they're separate like this? But what's going to happen is when they come together, they make H2, and they're going to share those two dots. Okay, now remember, if you're like, what's an analogy I could use? I'm trying to think of an explanation off the top of my head. I don't know. I don't know. I can probably only think of a really dumb example, but imagine if you live in a house, okay? I live in a house with my family, okay? If I go upstairs in the kitchen and I pull the drawer open, I'll see that there's, maybe 12 forks or something, okay? There's 12 forks. Are those forks mine? Do I say, when somebody comes in the kitchen, they're like, okay, Dad has 12 forks and nobody else has a fork? No, there are 12 forks, but they are shared amongst all of us, right? So we say the family has, 12 forks, okay? Well, that's the same thing here. In the hydrogen molecule, that if you're not paying attention, I need you to wake up just for 30 seconds here and just pay close attention, look deep into my eyes, and I will hypnotize you. It's like this hydrogen now has 2 electrons, okay? And it's like this hydrogen has 2 electrons. Now, what would be so great about that? Well, hold on. When hydrogen has 2 electrons, right? Hydrogen only has the 1s shell half full. When it has 2 electrons, it's going to be 1s2. And its valence shell is going to be completely full. It's isoelectronic with a noble gas. Aha! All right. Now, let me show an example that's a little more complicated, okay? Now, again, you can represent the bonding pair as 2 dots. I will implore you to not do that because Miss Dion doesn't like it, okay? And you're like, I don't care what you don't like. Anyhow, I don't like it. It's just not the way I do it. When you have 2 electrons, a shared pair, I like to represent them like this, like a line, okay? And I'm always going to do it that way. Let's look at another example. Let's look at if we have a hydrogen, and everybody by now should know that hydrogen has 1 valence electron. So there's the Lewis dot structure of hydrogen. Fluorine is in group 7A. It's got 1, 2, 3, 4, 5, 6, 7 valence electrons. Well, look, remember that hydrogen has to gain 1 electron to fill its valence shell, and fluorine has to gain 1 electron. Okay, what are they going to do? they're going to end up sharing these 2 electrons right here, okay? And that's what's drawn right here. They put those 2 electrons right there in the middle, okay? And that's why we end up with this molecule, which is hydrogen fluoride, okay? And we have this shared pair. So again, I'm going to repeat myself. It's like the hydrogen has 2 electrons, okay? So it's isoelectronic with helium, and it's like the fluorine has 8 electrons. So it's isoelectronic with neon. Give me a thumbs up if you're like, I don't know, 80% of the way with me or more. Like, yeah, I see what you're doing here. All right, good, very good. All right, great. I'm glad you're still paying attention too. All right. So let's go back to the covalent bond. I know we haven't looked at a lot of problems today. You know, I stand by my lecture. This is exciting stuff, okay? All right, so let's think about the properties of a covalent bond a little bit more, okay? And you need to know these 3 properties. I'll highlight all 3 of them. Okay, you need to know bond order, you need to know about bond energy, and you need to know about bond length. And if you're like, hey, Mr. Dion, we already talked about bond energy and bond length a little bit already today. You're right. You are right. Okay, but right now, let's shift our attention right on to bond order. Bond order, I think, is pretty simple. It says here, bond order is the number of electron pairs being shared by a given pair of atoms. A single bond consists of 1 bonding pair and therefore has a bond order of 1. So let me draw that HF molecule again. So if I draw the Lewis dot structure for HF, okay, hydrogen fluoride, look, what's bond order? Let's read it very carefully. It says the number of electron pairs being shared. Well, how many electrons are in a bond? Okay, how many electrons are in a bond? Not a trick question. I want somebody to answer this before I don't want to answer this for you. Yes, there's 2 electrons in a bond. Okay, because they're sharing the 2 electrons. Exactly. So 2 is a pair. So how many electron pairs are being shared? 1 pair. So that means that the bond order here is, I'll just abbreviate it BO, is 1. Okay, like that. Nothing more than that. Okay, nothing more than that. Bond energy, I bet you can all wrap your head around bond energy. It's the energy that's required to overcome the attraction between the nuclei and the shared electrons. The stronger the bond, the higher the bond energy. Well, come on, that's a no-brainer. I mean, you got 2 atoms attached together. The more energy that it takes to rip them apart, the greater the bond energy. Okay, and then bond length is the distance between the nuclei of the bonded atoms. So that's where we get bond length from. If you've ever seen a table of bond length before. There we go. We got 3 minutes. I'll cover this slide and then maybe we'll kind of check in at the end. It says here trends, right? You notice that general chemistry is very general, right? We like to talk about trends in general chemistry. It says for a given pair of atoms, higher bond order results in a shorter bond length and a higher bond energy. Well, that makes sense because you get more attraction. Not more attraction, what's the word? I was going to say more overlapping of orbitals, which is what it is, but I don't want to get too complicated. You got more bonds, right? If you got more bonds, then the atoms have to get closer together, okay, in order to form all those different bonds, and therefore you're going to have a shorter bond length. And it's going to take more energy to rip the atoms apart. Next point says, for a given pair of atoms, a shorter bond is a stronger bond. So the shorter the bond, stronger it is. As bond length increases down a group in the periodic table and decreases across a period, right? The reason bond length would increase as we go down a group is because atoms get bigger and bigger and bigger. The reason it would decrease going across a period is because atoms get smaller and smaller and smaller. And then the last one says bond energy shows the opposite trend according to Coulomb's law. Is bond length, is inversely proportional to bond energy. Well, we already looked at that today. Okay, so let me just go over one quick example with you here on this slide, and then I'll have to call it a day. Let's compare, let's compare a carbon-carbon bond. Oops, that's not a highlighter, is it? Let's compare a carbon-carbon single bond, a carbon-carbon double, and a carbon-carbon triple. Okay, well, what's happening to the bond order here? Okay, the bond order here, there's only 1 shared pair. So the bond order here is 1. The bond order here, there's 2 shared pairs. So the bond order here is equal to 2. And the bond order here is equal to 3 because there's 3 shared pairs. Look what happens to the length. Okay, I want to look at length first. Look at length first. So we go from 154 to 134 to 121. So that means the length is decreasing as the bond order is increasing, right? The more shared pairs you have, the closer the atoms have to get to each other to share them. The next one we'll look at is the energy, right? The more bonds that I have, the more energy it takes to break the two atoms apart from each other. So you go from here to here, all the way up to here like that. All right, 10:39. Should probably stop at this point. Here we go. Where are my students? Come on.